Hi, everybody. Welcome back to Statistical Methods. This is week 5 at this point, and this is lecture 1. And I'll be covering the final section of our introduction to hypothesis testing. And we'll do so by discussing one-tailed and two-tailed hypothesis tests, and by discussing some issues and debates surrounding null hypothesis significance testing. So we'll start out by talking about one-tailed directional tests. So when a research hypothesis is specifying the particular direction in which an effect will take place, we'll be conducting a one-tailed directional hypothesis test. So some example hypotheses of these one-tailed directional hypotheses are below here. So one, stimulating a certain brain region will enhance the display of empathy. So enhance in this case means to increase the display of empathy. Number 2, increased absences are associated with worse academic performance. Worse here is communicating lower academic performance. Number 3, symmetrical faces will be judged as more attractive than asymmetrical faces. So more attractive here is communicating higher attractiveness scores associated with symmetrical faces. So because we predict a specific direction for the effect, this means that we only care about extremity in that particular direction. So imagine if we tested our prediction that stimulating a certain brain region enhances empathy. So we would not count extremely low amount of empathy as support for a research hypothesis, even if the result we obtained was improbably low, with a p-value less than 0.05. So when our hypotheses are directional, we compare our obtained result to a cutoff score that isolates 5% of scores only in whichever tail we care about. So we'll be looking in that right tail if we predict an effect in the positive direction. So we'll be comparing to that z-score of positive 1.64 in the Shiny app to isolate that upper tail of the distribution. Now, on the other hand, if we predict an effect in the negative direction, we'll be comparing our result to a z-score of negative 1.64, which isolates this leftmost tail of the standard normal distribution to result in that p-value of 0.05. So this is a visualization of what these distributions would look like in the Shiny app and what our cutoffs would look like in the Shiny app for positive directional hypotheses and negative directional hypotheses. So this is fairly intuitive. Now, less frequently, researchers will want to test non-directional hypotheses about a relationship between variables, or an effect, without specifying the direction of this effect. So examples of this could be drinking coffee influences students' GPA. Now, using this word influences means that we could be looking for either a negative or positive influence on GPA. Similarly, early cohabitation, or living together with a partner, is related to a couple's likelihood of divorce, which means living with that partner could make it either more or less likely that they will eventually divorce. Now, in these cases, the researchers will want to count an extremely high or an extremely low result as evidence in favor of the research hypothesis. Thus, we want to look for the extremity in either of the probability distribution's two tails, hence a two-tailed test. Now, the important part here is that when we're conducting a two-tailed hypothesis test, we split the percentage of scores implied by the significance level. So if our significance level is 0.05 or 0.01, we split that between the two tails. So let's say we're isolating 0.05. We would split it so that we have 0.025 in this tail and 0.025 in this tail. And the z cutoff here is negative 1.96 or positive 1.96 that we're isolating for a two-tailed test. So we're not isolating 5% on both sides. We're isolating 2.5% when we're using that significance level of 0.05 with a two-tailed test. Right, so for a two-tailed test with a significance level of 0.05, the cutoff scores that will compare our obtained results to will be whatever values isolate 2.5% of scores in each tail. So why can't we just use 0.05 in both directions? Well, this increases something called type 1 error that we're going to discuss at a later point during the course. But for now, if we were to do this, this essentially makes our findings somewhat less reliable. So it's important to note whether the hypothesis is stated as a directional or non-directional hypothesis, because this changes the cutoff score that we'll be comparing our sample score to in step 5 of NHST to determine whether or not to reject that null hypothesis. For example, in an experiment using a significance level of 0.05, with a directional hypothesis, I will reject the null if my z-score is more extreme than positive 1.64, if I predicted more, higher, or greater scores in my alternative distribution, or more extreme than negative 1.64, if I predicted lower, less, or fewer scores in my alternative distribution as compared to that null distribution. But for non-directional hypotheses, I will reject the null if my z-score is more extreme than either positive or negative 1.96. So here is a visual representation of when and how the significance level, or rather the p-value cutoff, will change when we're using a one-tailed or two-tailed null hypothesis significance test. So using the example of coffee and academic performance, let's talk about how we state our research and null hypotheses for one- and two-tailed tests in terms of statistical notation. So if our research hypothesis, so what we actually predict, is that drinking more coffee will lead to higher academic performance, we're comparing again a distribution of academic students who are drinking coffee to a null distribution where drinking coffee has no effect. And we expect that our alternative hypothesis distribution, or mu1, so the mean of that distribution, will be higher in the drinking coffee distribution as compared to a null distribution, which should be just the same as the distribution of students who are not drinking coffee. Right, so notice the greater sign here for our one-tailed test. Since this is a directional hypothesis where we predict that more coffee will increase academic performance, the mean of the distribution in terms of academic performance scores of students who are drinking coffee is greater than the null distribution. Now, the null hypothesis associated with this particular research hypothesis is shown below. That the coffee distribution's academic performance score is less than or equal to the null distribution, mean 2. Or if our hypothesis is the opposite, but still a directional hypothesis, so drinking coffee leads to worse academic performance, the coffee distribution population here, that mean should be lower than the null distribution, if indeed coffee hinders academic performance, right? So if our research hypothesis is in that negative direction, we would like to see our alternative distribution, mu1, with lower academic performance scores than mean 2 of the null distribution. So to state the null hypothesis, mu1 is greater than or equal to mu2. Now let's say that we had a two-tailed test and a non-directional hypothesis. Coffee influences academic performance. Our research hypothesis would simply be mu1, the coffee distribution population, is not equal to mu2, or this null distribution. So in other words, there is some difference in academic performance between coffee drinkers and non-coffee drinkers. And our null hypothesis would then simply be that there is no difference between coffee drinkers and non-coffee drinkers in academic performance on average. On a quiz, I probably won't have you communicate hypotheses in this particular notation. But it is good to know how this would be communicated. Now, the Shiny apps that we used will always have an option for tailedness of the distribution, depending on what type of test we're using. And this circled in red box here is where you will change that tail. So of course, if you're dealing with a one-tailed test and you're trying to isolate that upper portion of the distribution, you're predicting that, let's say, coffee leads to higher scores in school. You want that one-tailed upper. If you're predicting that coffee leads to poorer scores, you want the one-tailed lower. And simply, if you're predicting that coffee has some, not specifying the direction, effect on academic performance, you would specify that two-tailed option in this drop-down menu here. And this will be the case for other distributions that we'll learn outside of the standard normal as we get further into the course. Now, one really important thing to note here is that when you're using a two-tailed test, it will automatically split the significance level between the two tails. So when you select that two-tailed option, you don't have to specify 0.025, specify the tail probability of 0.05. Because that will be done for you. Now, in the second half of this lecture, I'm going to talk about some issues with null hypothesis significance testing. So, as we previously stated, we're going to focus on NHST throughout this course, since it is the way that most social scientists have done statistics for decades. So, understanding this isn't crucial for interpreting most published research, but it's really important to note that the field's heavy reliance on NHST and p-values is not without any controversy. So I'll cover some of the major critiques of NHST now and how they'll be addressed in this course and how they're somewhat being addressed in the field. Now, for much of the history of the social sciences, there was a near exclusive focus on p-values as the single most important statistic to come out of a study. So finding a p-value less than 0.05 was this gold standard that allowed you to say that you found an effect, or in other words, that your research hypothesis was supported by the data. And then you can get your paper published if you have that p lower than 0.05. Now, this over-reliance on p-values is problematic for several reasons. Number one, it leads to difficulties in interpreting results, and p-values are often misinterpreted. So as we know, a p-value tells us the probability of finding a result as or more extreme than ours, assuming that the null hypothesis is true. So if there's really no effect present, how likely would it be to obtain the data that we did, or data more extreme? So essentially, the probability of our data, given that the hypothesis that we have is not true, or in other words, that the null hypothesis is true. And this takes some mental gymnastics to try to wrap your head around. But p-values are regularly misinterpreted as the probability of our research hypothesis being false, or the probability of the null hypothesis being true. And this is not the case. A p-value tells us just this, and this is pretty much the only way you can state it. The probability of finding a result as or more extreme than ours, assuming that the null hypothesis is true. How likely would it be to find data as or more extreme than the ones that we've obtained if our research hypothesis is not true, or the null hypothesis is true? Not the probability of our research hypothesis being false, and certainly not the probability of the null hypothesis being true. Now, these mistakes are, of course, made by students at times, but they're also made by psychologists and other social scientists who use these statistics. And methodology researchers have published a number of papers examining the misinterpretation of p-values by actual scholars in the fields. So the narrow and technical definition of p-values conflicts with people's intuitions about the information we actually want to obtain, which is how likely is our hypothesis given the data. So we really don't get that from null hypothesis significance testing. Instead, we get how likely are the data we obtained given the null hypothesis being true. We really can't make statements about how likely our hypothesis is, our research hypothesis, given the data we obtained. Now, another point is that p-values do not communicate effect size alone. So in first learning about p-values, people often want to interpret it as a measure of effect size, or in other words, how strong an experimental manipulation or association between variables is. So for example, finding a very small p-value like p equals 0.0001 must be stronger in terms of effect size than finding a p-value of 0.04. Now, this is not always true because p-values actually decrease as a function of sample size increasing. So holding effect size constant, a sample with n equals 1,000 subjects will have a smaller p-value than a sample with n equals 10 subjects, even though the effect size is actually the same. And we'll see why this is specifically later in the course, but for now, know that p-values do not communicate effect size alone. Now, a third point is that null hypothesis significance testing forces us to use all or nothing or binary decision making. The use of significance levels in null hypothesis significance testing only allows for one of two conclusions. If the p-value we obtained is lower than the significance level, we reject the null hypothesis and interpret our results as support for our research hypothesis. But if the p-value is greater than or equal to that significance level of 0.05, we fail to reject the null hypothesis and our results are inconclusive. But in actuality, is the difference between p equals 0.04 and p equals 0.06 always meaningful? Probably not. Thus, P is not a good graded metric of evidence for a hypothesis, because we have to make this binary decision to either reject the null hypothesis, communicating support for our research hypothesis, or we simply fail to reject that null hypothesis and our results are inconclusive. Now, some researchers think that P is less than 0.05 might not be a stringent enough cutoff. So some have argued that a P less than 0.05 can often be found even with fairly weak or small effects, especially when sample sizes are large, because remember that p-values decrease with large sample size. So some have argued that the statistical significance level should be redefined to a more conservative value, like p equals 0.005. Some have even said p is less than 0.001. Now, a really important thing about NHST and how it's used in the social sciences that really brings down its credibility is unmet assumptions. So as we will learn later in this course, statistical tests using null hypothesis significance testing often necessitate that a number of assumptions about your data and your particular experimental design are met. For example, they assume that data are normally distributed. So issues of skewness can become problematic when you're using null hypothesis significance testing. Also that the standard deviation is more or less the same across experimental conditions. And that variables are measured on equal interval scales. In practice, however, these assumptions are rarely discussed in research articles, and they may be difficult to meet, bringing the validity of the results of these tests into question. Just looking at this last point here, that social scientists should be using equal interval scales. Most of the measures we use are Likert type items, so like 1 to 7 scales. Self-report items, which could be treated as equal interval scales to some extent, but more realistically reflect ordinal scales of measurement. Yet researchers treat them all the time as if they're equal interval scales, which could lead to issues interpreting NHST. So I don't want to leave you simply with problems. What could be some solutions or alternatives to NHST? And how should we deal with these issues in the context of this course? So one solution is to calculate and report effect sizes, not just p-values. So there's no good reason to report only p-values and treat them as the single piece of evidence that matters. Fortunately, there are various statistics to quantify effect size directly, which are free from influence of sample size. And these allow us to gauge the practical, not just statistical significance of an effect. So some of these effect size estimates are Cohen's d, which is simply how many standard deviations apart are our group means. So if I were to assign one group to receive a steady regimen of coffee before every test they took, and another group to drink water or some neutral beverage, how many standard deviations apart are the group means on academic performance? That is a Cohen's d. Now, probability of superiority is another effect size estimate. So if I were randomly going to pick somebody from group 1, the group that received coffee, and compare their score to somebody from group 2, the no coffee group, what is the probability that their score would be higher in that coffee group than the non-coffee group on whatever measure of academic performance I'm using? And the final type of effect size estimate we'll talk about are the R-squared or eta-squared type of effect size, which communicate what percentage of variability in the dependent variable can be accounted for by variability in the independent variable. So in other words, what percentage of variation in academic performance can be accounted for by variation in drinking coffee? So another solution would be to use a lower p-value threshold. So as we previously mentioned, people want to redefine statistical significance to a lower value, like 0.001 or 0.005. Now, the most extreme alternative would be to use a different statistical framework entirely, like Bayesian statistics. Now, Bayesian statistics is a different approach that allows for more easily interpretable statistics. For example, a ratio of the probability of our research hypothesis to the probability of the null hypothesis being true, given the observed data. So this is what people intuitively want, and this is how they often misinterpret p-values. What is the probability of our research hypothesis given the data we've obtained? And conversely, what is the probability of the null hypothesis being true given the data that we've obtained? So this is an odds ratio called a Bayes factor. This communication of a ratio of the probability of this research hypothesis to the probability of the null hypothesis being true given those observed data. Now, most but not all of the conclusions reached by p-values and Bayes factors will be the same, but unlike null hypothesis significance testing, Bayesian statistics also allows us to make statements about the probability of the null hypothesis. So when we want to garner evidence for the absence of an effect, or in other words, drinking coffee has no influence on academic performance, we'd be able to make probabilistic statements about that being true if we were to analyze data with Bayesian inference. Now, Bayesian inference is slowly gaining traction in the social sciences, but it's not often taught in undergrad statistics courses. And realistically, I'm not sure if it ever will become a standard practice. But I've also given you some ideas for how we can improve our current paradigm for analyzing data, which is null hypothesis significance testing. So though understanding p-values and null hypothesis significance testing methods are crucial to interpreting the published literature in the social sciences, they are not the only way to present evidence for a hypothesis, and they're not the only thing that we should base our conclusions on. Now, p-values should be considered alongside other metrics of evidence when drawing inferences from studies, such as effect size estimates.